everyone, and welcome, and thank you for joining us this morning for this latest installment of the Dean's Distinguished Women in Math, Statistics, and Computer Science lecture series. In case you don't know me, my name is Christiane Lemieux. I'm the Associate Dean Operations and Academic for the Faculty of Math, and I'm really happy to be here to give a few brief opening remarks on behalf of our Dean, Mark Giesbrecht, who unfortunately could not be here this morning because he's out of the country, and I was disappointed to miss this lecture. I'd like to start with a land acknowledgement. So much of the work we do here at the University of Waterloo takes place on the traditional territory of the neutral Anishinaabe and Haudenosaunee people. Our main campus is situated on the Haldeman Tract, which is the land that was granted to the Six Nations and includes 6 miles on each side of the Grand River. And our active work towards reconciliation takes place across all our campuses through research, teaching, learning, and community building, and is coordinated within our Office of Indigenous Relations. So the lecture today is jointly presented by the School of Computer Science, Women in Computer Science, and Women in Math. And since our inaugural lecture that took place in January, I'm really thrilled to highlight the outstanding work of prominent female researchers to this lecture series. And I'd like to especially thank Women in Math for coordinating this lecture series and working with the departments and the school to make it happen. Both Women in Math and Women in Computer Science are doing really amazing work to support, promote, and advocate for women in our fields. And their work is really important because even if there's been a lot of progress towards equity and representation in the last few decades, women are still underrepresented in math and computer science. So we're really grateful for all the work they do. So without further ado, I'd like to introduce or pass things over to Professor Gautam Kamath, who will introduce our speaker.
And yeah, it's my distinct honor and pleasure to be fortunate enough to introduce Professor Virginia Vassilevska Williams. Virginia grew up in Bulgaria, but she moved to the US. She studied her bachelor's at Caltech, her master's and PhDs at CMU. She did postdocs at IS at Princeton, Berkeley, Stanford. She was faculty at Stanford, an assistant professor there for a few years before she moved to MIT, where she's now a full professor. So basically, she's done a tour of all the top schools in the US. She's also received all the accolades. In her early career, she received the CAREER Award, Google Faculty Research Award, as well as the very prestigious and selective Sloan Fellowship. And this continued as her career progresses, including more recently the Simons Investigator, which is a super prestigious research. A lot of top researchers that I really respect a lot have received it, including Virginia. But these are just titles, and I want to tell you a little bit more about her incredible contributions to research. She has super broad expertise. Like, I won't talk about computational social choice things or her work on anything graphs, but she's still world experts in this. Yet just last week, we were lucky to have her student Greg Godwin, who's now a faculty at the University of Michigan. He started his work in this area with Virginia. Now, he's grown up and he's like recognized in his own right as a world expert. And it's all thanks to Virginia's excellent advising. Today's focus is going to be on fine-grained complexity, which Virginia is a pioneer in. It's frankly had a bit of a moment in the algorithm complexity community, some of these questions in the past are, very hard, requires years or decades of study to even get started. But Virginia, I think, made some breakthrough contributions that really propelled a lot of interest and excitement in the field. Yes, given a lot of insight into a lot of fundamental, foundational computational problems, which we really didn't understand quite as well as we do now before. And so in 2015, she organized a program at Simons, which is a semester-long program focused on this research agenda. And I'll say in 2018, she gave an invited talk at the International Congress of Mathematicians. This is a really big deal. This is only held once every 4 years, and theoretical computer science is only a small part of that. They only invite, a few select most exciting mathematical areas in all of theoretical computer science, and only the most prominent people in that area to give talks on it. And Virginia was recognized and invited to give a talk on that. This is an app description. She was recently won the 10-year Test of Time Award for some of her work at FOCS 2014. I'll mention a little bit more of my own personal experience. Most people tell you their first time meeting someone. I'll tell you my first time failing to meet Virginia. So, STOP 2012, this was my first conference. I was last year undergrad. And there was this one big result everyone was talking about. This is a new breakthrough result on fast matrix multiplication, which Virginia is an expert on. I was super excited to see this talk. Virginia, she wasn't there. Her postdoc supervisor gave the talk in her stead. And this is really unusual because she was like a postdoc at the time. It was a solo author paper. This should be a career highlight for anyone at that stage. What turned out was going on is that Virginia was in labor at the time with the birth of her child. And I think this really highlights some of the challenges that women in our community face. This is, again, it's easy to say now she's like a very prominent researcher, but at the time I can imagine that would be a very tough spot to be in. Like it feels like you're missing out. But of course, Virginia's brilliance has persevered nonetheless. Let me say, besides research, she's also been a great community member. I was a grad student at MIT, and every Wednesday night, she organized something known as Music Night, where we would get together, play drums, keyboard, guitar at varying levels of skill, myself very poorly. And she brought like food for all the hungry grad students, which is a very kind gesture of her. I haven't found anything that really replaces that. Beyond MIT's community, she's also been involved in founding an organization known as TCS for All, formerly TCS Women, which really brings together and builds these communities of people who are underrepresented. And I don't know, she's just a brilliant community member and researcher in every sense of the word. So after this, after a lot of ado, let me pass it off to Virginia. Thank you very much.
Thank you very much, Gautam. I'm really humbled. I just feel, thank you. That's so sweet. I'm really excited to be here. Thank you very much for inviting me. And I want to tell you about fine-grained complexity, an area that I've been working in for a long time now. So let me start. So what is it that we want to do in algorithms? Okay, I teach algorithms classes and we teach a bunch of techniques. And the question we really want to know the answer to is how fast can we solve certain fundamental questions, some fundamental computational problems in the worst case. Right, and there's a lot of these textbooks written, I can't possibly fit them here, with different techniques that you can use to solve different problems. Okay, and often you see a problem and you just apply a combination of these techniques and you get some output. Now, how fast do we want to solve a problem? So imagine a computational problem, you're given some instance, let's say a graph in which you want to find shortest paths. The size of your input is n, and what you really want is to get an algorithm whose running time is linear and the size of the graph linear, because we typically have to read the input. Okay, by and large, right? And the good news is because we have these huge toolbox of techniques, we can solve many problems in almost linear time. It's great. And here's a bunch of problems you may have seen or taught in algorithms classes. And nowadays, there have been a lot of breakthroughs, in particular for max flow, where you can get almost linear time algorithms with brand new techniques. So we build new techniques all the time. And really, this question about how fast we can solve problems is very old. So, for example, Gödel wrote a letter to von Neumann in 1956, and he was thinking about problems that do have algorithms. So problems like in NP and so on. So there's some underlying search space, and you can always kind of brute force the search space. That's the exhaustive search algorithm. And he wanted to know how much can you beat this brute force algorithm that always exists? And in general, we really want to get as close to optimal, as close to linear time, but sometimes, we don't even know how to beat the exhaustive search algorithm. All right, so unfortunately, even though we have some very, very important problems in the exhaustive search, the brute force algorithm is trivial to come by. So you just look at the definition of the problem and that tells you how to solve it, there's actually almost no improvements over the brute force algorithm, even though we've developed many techniques. Right, so I will call a problem hard if there's a very easy algorithm the moment you see the definition, but we can't seem to beat it. So these problems are very important. They come from all over the place, from computational biology, geometry, you name it. There's a lot of these nice problems. As I said, typically you can come up with a very simple algorithm. Often it's exhaustive search, but sometimes it's not. Sometimes you just apply some technique you've seen in algorithms classes like dynamic programming and so on, and you get an easy algorithm, some textbook algorithm. But unfortunately, when you analyze the running time of these algorithms, they turn out to be super slow, right? And then you go on the internet, you ask ChatGPT whatever you want, and what do you get? You see that people have tried to solve these problems and improve these textbook algorithms for decades and gotten no improvement. And so this is why I call these problems hard. So I will give you some examples. The first example, the canonical example we teach in our algorithms courses is a problem called K-SAT. It's a problem from logic. So we're given n Boolean variables and a formula which consists of clauses, m clauses. They're all ANDed together, C1 and C2 and so on. Each clause looks like this. It's an OR of variables or negations of variables. They're called literals. And what do you want to know? You want to know is there Boolean assignment to these variables so that every clause is set to true once you plug in the Boolean assignment. You see this problem. What is K? K is the maximum number of literals, maximum number of variables or negations in a clause. So K can be a constant or larger and so on. There is a very trivial algorithm, the exhaustive search algorithm. The search space is all the possible Boolean assignments to the n variables. Each variable can be true or false, so there's 2 to the n of these. For each of them, you try it and plug it into the formula. By plugging in, you just plug in the value, and just in linear time of the formula, you can see if all the clauses are satisfied. This is a 2 to the n times the length of the formula sort of algorithm. The best known algorithm is a little bit faster. So is this 2 to the n, which is the brute force running time, minus some constant, like 2 or 3, times n divided by k, which is the number of literals in a clause. Okay, and what people, and times a polynomial m to the d, and m is the number of clauses, so basically the length of the formula. So what people try to do is, for each fixed k, try to improve the c, okay, and get faster and faster algorithms, maybe improve the d, but this is basically the running time, and you can see that when k becomes non-constant, you essentially recover the brute force algorithm with some very tiny improvements. Okay, if this thing goes to 2 to the n as the width of the clauses grows, which is very annoying. And you can say that we do not have a 2 to the n to the 1 minus epsilon time algorithm for any epsilon bigger than 0. So if we want to beat the exhaustive search algorithm, we really want an improvement in the exponent. Getting such tiny improvements here when imagine k is log n, this is nothing, right? Almost nothing. We want something that's 1.999 to the n, or try to get to linear time even. But even just beating exhaustive search in this sense, this is something we really want. And we don't know how to achieve current techniques.
Question. What is that algorithm from? How old is that? That's known algorithm?
They keep improving the constants. Every year there's some improvement. For each k, there's an improvement. There's a general sort of thing here that works for every k, and there's a particular constant. And I think in the last 10 years, there was an improvement there too. But people work on this actively. And actually, there's even more interesting question about this. Why should this be sort of the expression? Why shouldn't we be getting a better improvement besides n over k? Why can't we get n over k log n, for example, or something? N log n over k, sorry. There's something better and better, but even that's not known. So this is sort of the best known sort of expression. All right, But this is SAT. SAT is a notoriously very, very difficult problem. So what I'm going to give you now is a different problem that you may not think is difficult, but I think it's hard. Okay? Here's this problem. So this is the longest common subsequence problem. You're given two sequences of letters, let's say A, C, T, G, some finite alphabet, and you want to find a subsequence, so a string of letters that appears in both of them in the same order, maybe skipping over letters, and that has maximum length, right? So here's an example for this. The blue letters form a subsequence that appears in both of these sequences. The red ones are, mismatches. You can think of it as an alignment problem. You want to align the two sequences on top of each other, maybe with some gaps, so that you can, the blue parts is basically the similarity between these two sequences. Okay? So this problem comes from a lot of places. It has applications in computational biology, where, for example, you may want to know how similar two DNA sequences are under this notion of similarity. Or in spell checkers, maybe you're given some word and you have some dictionary, and maybe the word is misspelled, and you want to see whether there's a real word that matches it. Maybe some characters were changed or replaced or deleted or inserted, so on. So what do we know about this problem? This is a classic example of problem that can be solved with a technique called dynamic programming, and we teach it in our algorithms courses. And the dynamic programming algorithm runs in quadratic time in the length of a sequence. It's n squared. The best known algorithm is from the 1980s and runs in n squared over log n squared time. So there is a tiny improvement over this n squared, but it is not 10 to the 1.9, and it is not linear. And n squared, you might think, oh, it's such a tiny polynomial time, but imagine someone tells you, okay, I have the human genome. I'm not going to run it of the whole human genome, but maybe, like 1% of it. Okay, that's a billion, and now 1%, okay, maybe it's 10 to the 7. But when you plug it into n squared, it becomes completely infeasible. So nobody is going to run this algorithm unless your input is very tiny. And here, what we want to know, so this is the textbook algorithm, what we want to know is, can we beat it in the exponent? So can we get something like n to the 1.9? So more generally, is there an epsilon bigger than 0, so that you can get an algorithm that runs in n squared to the 1 minus epsilon time? And this is where these two problems are very similar, SAT and longest common subsequence. There's a natural algorithm for them. And with some t of n time, and getting t of n to the 1 minus epsilon seems difficult for the current techniques. All right, so here is a summary. We have problems where our current techniques get stuck. They come from very different areas. They have simple, often exhaustive search text-based algorithms. They run in some t of n time. That's much more than linear. Could be exponential, even more. And we don't have significantly faster algorithms, even though people have worked on these problems for a very, very long time. And even though we have new techniques that come up, but we haven't been able to use them to solve these problems. What do we want to know? Why are we stuck on these problems? And more interestingly, are we actually stuck because of the same reason? Could it be that secretly these problems, even though they look very different and come from different places, maybe they're the same problem. And maybe the reason why we're stuck on them is the same. And once somebody comes up with an algorithm that solves this structure that they have in common, all of a sudden we'll solve all of them. That would be great. Or maybe we'll show that one of them is difficult and actually cannot be solved, and we know that none of them are solvable. Okay. So the plan for the rest of the talk is I'm going to tell you a little bit of some traditional hardness and complexity theory and why it doesn't quite solve the problem we want to solve. Then I'm going to tell you how to slightly change what's going on here to get an approach that gets closer to resolving this problem. And then at the very end, I'll tell you about some new developments that we have from the last year. Okay. Any questions on this point? Oh, yeah. Space is, yes, so we're not going to be addressing space here, but you can address space with a similar approach. That's a good question. All right. Good. So let's talk about the traditional hardness. First thing is, in complexity, there are these very strong time hierarchy theorems. And roughly they say that for any nice function, T of n that you have, for example, T of n could be n to the c, for some fixed constant c, there exist problems that can be solved in n to the c time or T of n time, but you cannot solve them provably. They cannot be solved faster than that. So there exist these hard problems, right? We can show them with diagonalization and so on. Unfortunately, these problems that you get from the time hierarchy theorems are not the problems we typically care about. The problems we typically care about cannot be shown to be hard in the same way. And in particular, let's say we just look at K-SAT, which I mentioned here, there's no proof that SAT cannot be solved in linear time. So it is completely possible that there's a linear time algorithm for SAT, as far as we know. Even though there exist these hard problems for any, even for 2 to the n, there exist problems that are in 2 to the n time, but not less. So this, even though we know how to prove time hierarchy theorems, we cannot seem to address the question of like, why is longest common subsequence stuck at n squared time and why is SAT stuck at 2 to the n? Okay, so another type of hardness is NP-hardness, right? So we have the classes P and NP, classes of problems. P are all those problems that can be solved with running times that are polynomial in the size of the input, and NP are problems whose solutions can be verified in polynomial time with the size of the input. And a very important question is P equal to NP? And for whatever reason, people believe P is not equal to NP, okay? Almost everyone you ask, they'll say P is not equal to NP. Why? We don't know. But yeah, it's a notoriously hard problem. If you resolve it in any direction, you get $1 million, infinite fame, full professorship wherever you want. It's all nice and good. And as we know from Cook, Levin, and then Clark in the 1970s, K-SAT is NP-hard. And that's why we really, really think this problem is hard. What does this mean? It means that if you somehow come up with some algorithm for a K-SAT that runs in polynomial time, then all of a sudden every single problem in NP also has a polynomial time algorithm, NP equals NP, and you get $1 million. Okay, so we believe that SAT is hard, so it cannot be solved in polynomial time. It's conditional hardness. It is really just based on an assumption. P is not equal to NP. It doesn't mean that SAT doesn't have a polynomial time algorithm. It's just that under our assumption, this is true. Oops. Now, why is this not sufficient for us? Well, okay, let's go over here. What does NP hardness of a problem mean? It means you assume P is not equal to NP. Then you show that if Q had a polynomial time algorithm, you can solve it you can use it to solve every problem in NP in polynomial time. And if you assume P is not equal to NP, then you conclude that this problem Q requires superpolynomial. Now we have an issue here with this approach, because if you wanted to show that a problem like longest common subsequence cannot be solved since a quadratic time, you will have an issue, because our problem already has a polynomial time algorithm. So it cannot possibly be NP hard. You cannot use this approach to show hardness for problems that are already in polynomial time. Also, this is really about just polynomial time solutions, and we just want to know for SAT, for example, why can't we beat the brute force algorithm? And the brute force algorithm is 2 to the n, which is very far from polynomial. So it doesn't answer that question either. So we want problems that are in n squared time to be hard, And this approach, although it nicely says, oh, if we believe that P not equal to NP, then SAT is hard, it doesn't actually talk about the running times that we care about. So it is too coarse-grained. All right. Now, I want to take a step back and talk about why is it that we think about polynomial time as efficient in computer science. So often we teach our algorithms courses and we say, oh, we got a polynomial time algorithm, it's efficient, but why? Okay, so the first reason is because it allows us to forget about the model of computation, okay? The model of computation, if you use a random access machine, or use a pointer machine, or use whatever, a Turing machine, any machine that captures some computational device, to go between these models of computation, you get a polynomial overhead. Okay, there's some polynomial overhead. So if you got a polynomial time algorithm on one model, it implies a polynomial time algorithm in the other model. Okay, so we can forget about the model of computation. It's very useful. Also, because we like to run algorithms that use other algorithms as subroutines, if the subroutine is a polynomial time algorithm and we run on top of it the polynomial time algorithm that calls these subroutines, then it will still be efficient if polynomial means efficiency, because a polynomial of a polynomial is a polynomial, therefore it's all nice and good. But no one would say n to the 100 is efficient, okay? And no one would even say n squared is efficient. It is not really efficient if you actually care about running the algorithm on a really large input. Okay. This is just for theoretical convenience. Right. So what we're going to do, I'm going to give you this fine-grained approach. It will mimic NP-hardness in the sense that it's conditional and it will be based on reductions, as I'll mention later. But actually we'll care about the concrete running times. And we'll try to relate different problems with associated running times together and try to show some equivalences. Okay. Questions at this point? Actually, I'll go to the plan. Questions? All right. So now I'll tell you the fine-grained approach. So the way I'm going to do it is I'm going to contrast it to NP-hardness. So we'll have NP-hardness on one end, and we'll try to show you how it's similar, how it's different. Okay, so here's a very high-level view of what NP-hardness is. You have some hardness hypothesis, namely P is not equal to NP. That happens to be the same as the hypothesis that SAT requires superpolynomial time. Okay. Then you build a special algorithm called a reduction. Now, this reduction, this is not the definition of a reduction, this is just a consequence of it. So it says that under this assumption, if you had the polynomial time reduction, let's say from SAT to Q, where Q is some problem, then the reduction will imply that if Q had a polynomial time algorithm, then you can use that polynomial time algorithm to solve SAT or any problem in NP in polynomial time, and therefore, with this reduction, you obtain conditional hardness. Assuming that P is not equal to NP, then Q also must require superpolynomial time. So this is basically the three steps of the thing. So here is how fine-grained hardness is done. First, you pick some hardness hypotheses, maybe just one, which have the following form. You have some problem H that you really think is hard. What does hard mean? It means that there's some running time, H of n, for inputs of size n, so that you cannot solve H faster than H of n times. So the fastest you could possibly do it, solve it is H of n minus, in exponent of 1 minus little of 1. Some tiny improvements, so polylog H of n, for example, is okay, but you cannot get H of n to 0.999. And on top of that, this hardness assumption is on a particular machine model. For example, the random access machine. So you fix your model, and now you make an assumption about some hard problem on that model. And everything we talk about in fine-grained complexities for that particular model that you picked. You can pick any model, but you got to stay in it. Okay, because going between models gives you an overhead. All right, so you make this assumption. Then you define some sort of different type of reductions. And I'll go into each of these steps later so you can see in detail. But what is the consequence of a fine-grained reduction? A fine-grained reduction is an algorithm that transforms this hard problem H, an instance of hard problem H, into an instance of some other problem that you care about, problem Q. And as a consequence of this reduction, it says that if you can solve problem Q faster than Q of n time, where Q of n is its textbook algorithm, then you can also solve H, the hard problem, faster than its hard running time, H of n. And how much faster? Here, Q of n, you save epsilon in the exponent, and for H, you save a delta in the exponent. They could be different, but for any epsilon that's bigger than 0, there exists some delta for which you can beat H's running time bigger than 0. Okay? So this, and now I'll go through this in a little bit again. So this is kind of the difference. Here, we only care about polynomial running times. We don't actually care how big of a polynomial blow up you get. But here, we actually really care about savings, how much you save over the natural running time of the problem. And finally, using this hardness assumption, you get conditional hardness. You say that if you believe H requires H of n time, then Q must also require Q of n time in this computational model that you picked. Okay? Questions here? Yeah.
Sorry, but the little O of 1, what's that?
So little of 1 can be, imagine I'm allowed to improve over H of n, for example, by polylog of H of n, or 2 to the square root of log of H of n, something that is subpolynomial. So you're not allowed to, this means that there is no H of n to the 1 minus epsilon time algorithm, where epsilon is bigger than 0 and is a constant. But you can have some improvements, like I'll show you in a little bit. Yeah. Good. Yeah.
So this plan is for NP-hardness, but some power of NP-hardness comes from completeness, actually.
And we'll have that in a sense. We'll have a similar notion of completeness, but problem-centric. That's another difference. Yeah, completeness basically means that there's reductions in both directions.
Yeah, and you're saying you have that here also.
We'll have it, we'll see. Yeah. In some cases. Yeah.
Does most of the community agree on like what the right computation model is, or is it divided?
No, I don't think they're divided. And by and large, we usually pick the word RAM, but you know, there's work on the real RAM and many different models. It just depends on what model your reduction works in. Right. Okay, so let me go into detail. So what I'm going to do now is I'm going to tell you about the hardness hypotheses that we use by and large. Then we'll look at the two types of reductions, and you'll see what the actual definition of a reduction, and then I'll show you some results. Okay, so I've been saying this over and over, SAT is considered very hard. Okay, we know it's NP hard, but actually there is a hypothesis that postulates that it's not only NP hard, but it actually cannot be solved faster than 2 to the n time. Okay, so what is the actual hypothesis? It appeared in Pagliazzo Parturi in 2001, but the name strong exponential time hypothesis was actually given in 2010, even though the hypothesis from earlier. Okay, the hypothesis says, for every epsilon for which you claim you have a 2 to the n to the 1 minus epsilon time algorithm for SAT, I can give you some k, a width of the clauses, so that KSAT actually cannot be solved in the running time that you claim. So as the width of the clauses of KSAT grows, the longer and longer the clauses get, basically you cannot beat 2 to the n by significantly. As the length of the clauses starts to depend on n, you're essentially paying the brute force running time. So this is the strong exponential time hypothesis. It is much, much stronger than P not equal NP. P not equal NP just says SAT needs more than polynomial time. This says not only does it need more than polynomial time, but you can't even break the 2 to the n algorithm in the exponent. Yeah. Yes.
The k greater than or equal to 3, if you stick in 2, you are playing games with the details of the C's and D's from multi-slides ago. That's what's going on?
So, so for k equals 2, we have a polynomial time algorithm, right, for SAT, to SAT, so that's why.
Sorry.
So that's why.
Sorry, I was even fine.
Yeah.
Forget it. I was off on some other aspect and just.
No
Obviously,
worries.
it's a linear. Polynomial is linear.
Yeah, essentially, yeah. But yeah, basically k is already, k equals 3 is hard, but then it gets harder and harder.
So my head is not the correct.
No, it's fine. It's a lot of words. Any other questions? Yes.
Sorry, if this is true, doesn't that mean that P and NP are not equal?
Yeah,
So,
and indeed, yes. It means a lot. Not only, so if this is true, P is not equal to NP. Yeah, but we don't know how to prove P not equal to NP. We don't even know how to disprove this. This is the whole point. This is so much stronger, P not equal to NP, but it's still completely conceived. It could completely be true. Actually, a lot of us don't believe it's true. It's basically a challenge. You postulate this hypothesis, try to resolve it. So you can view this theory that way as well. Okay, so there's one hypothesis, right? And it's nice because it talks about running time. As I said, it's much stronger than P not equal to NP. Now, besides this hypothesis, there's actually 3 others that are widely used. Why 3, why not 1? I'll get into that in a little bit. So here's 3 others, and they're centered around 3 problems. You fix your computational model. Computational model here is the random access machine, where if you have integers with order log n bits, you can do certain operations in constant time. And you can change the model, and similar things would hold as well. So here are the 3 problems. The first problem comes from computational geometry. Okay, it's called the 3-sum problem. You're given n numbers. Here they're integers. And you want to know, does this set of n numbers contain 3 numbers that sum to 0? Okay, it can trivially be solved in n cubed time, because you can try all triples, but actually it can also be solved in n squared time. One simple way to do that, it's a randomized way, but you can also do it deterministically. You can just take all the numbers, negate them, and hash them. And then for every pairs A plus A and B, you compute A plus B and check whether A plus B is in your hash table. That takes expected n squared time, but it can also be done deterministically with pre-sorting the numbers and running some sort of other algorithm. So there is a faster algorithm. Baran, Domain, and Petrashko in 2005 showed that you can get an n squared over log n squared time for integer inputs. And this is your question about the n to the little o of 1. This log squared of n is a savings of a little o of 1 and n to the little o of 1. It's very tiny. Timothy Chen in 2018 showed that if you change the model to the real RAM model, now you deal with reals instead of integers, then you can get the same algorithms for real numbers, the same running time in the real RAM model. The 3-sum hypothesis says that yes, you can shave n to the little of 1 factors like here, but you will not get n to the 1.999. And this hypothesis essentially came from the computational geometry community a long time ago in the 1990s. And there are many papers that take this problem and reduce it to many other problems, showing that if you believe this problem 3-sum is hard, then a lot of problems in geometry are very hard. So this is a very old approach. Okay, here's a different problem. All right, here, this one, you have n vectors, and these vectors are Boolean. They have 0, 1 coordinates, and they're very short. Every vector has think of log n squared indices. So its length is log n squared. This means a little bit more than log n. And what you want to know is, does your set of vectors have two vectors that are orthogonal? Meaning in every coordinate, at least one of them is 0 because both of their Booleans. Okay, this problem has a trivial n squared times d algorithm, where d is the dimension. You try every pair of vectors, compute their inner product, check if one of them is 0, trivial. But the best known algorithm from 2015 has this sort of running time. If you look over here, d is the length of the vectors. If d is much more than log n, so it's, let's say, log n squared, this is, the savings is 1 over log n, okay? So it is not a constant here. So it's 2 minus 1 over log n, very tiny. So there's this hypothesis called the orthogonal vectors hypothesis that says, sure, you can get some tiny improvements, but you will not get n to the 1.999. And where does this hypothesis come from? Actually, okay, I'll tell you in a bit, but basically this hypothesis is implied by the strong exponential time hypothesis. If you believe that SAT requires 2 to the n time, then orthogonal vectors definitely requires quadratic time. There's actually a nice reduction there. Okay, the final problem here, yeah.
Having a hard time parsing that number, does that at least means you can always get OT ln s squared regardless of d?
Yeah, so if d is c log n, you'll get n to something subquadratic. So if
But quadratic, you're always getting it no matter what, because the easy algorithm has a d factor.
it has a d
I
factor.
think that's not even necessary.
Yeah, you can even get better than that. Yeah. Yes. So this is very nice, but it won't get you 1.9. All right. Final problem. And you, probably in the back of your mind, you'll be like, why are you giving me all these problems? Why isn't there just one? Okay, I'll also think about that. And we'll talk about this in a little bit. So the last one, we also teach it in our undergraduate courses, is the all pair shortest path problem, right? It's you're given a graph, n vertices, every edge has some, let's say, positive integer weight. And I want to know for every pair of vertices, what is the distance, the shortest path distance here. This problem has many algorithms, and almost all of them, the ones that we teach, run in n cubed time. There's Floyd-Warshall. If the weights are positive, you can run Dijkstra's algorithm for every vertex. There's a lot of these versions, and they all run in n cubed time when the graph is basically dense. Ryan Williams in 2014 showed that you can get something much better than n cubed. You can get n cubed divided by an exponential of a square root of log n. So this is faster than n cubed over polylog n for any polylog, but it is still not n to the 2.9. And because of this, we have this hypothesis from graph algorithms that says that this problem requires n cubed time, basically. You can shave a little bit over n cubed, but you won't get 2.99. All right. As I mentioned, this problem, you can use it instead of SAT, because you can reduce SAT to this problem, to orthogonal vectors, so that if you can solve orthogonal vectors in n to the 1.9 time, then SAT is in 1.99 to the n. So you can beat 2 to the n as long as you can beat this one. In fact, this is probably a harder problem. So strong ETH could be false, and this could be true. So very possible. All right, so now to the question, why is it not just one problem? Actually, it turns out that there's a strengthening of the strong exponential time hypothesis called the non-deterministic or common deterministic strong ETH, formulated in 2016 that, I don't know if it's true, but no one can disprove it. And in order to actually collapse these into a single problem, you must disprove it. So if you believe this hypothesis here, which I haven't defined, these will have to be different. And the theory we're building because of this is really problem-centric. So what's going to happen is that we'll have these equivalence classes, but they'll be centered around particular problems because we don't know how to collapse them into a single one. And there's some barriers to it. Okay. Questions? Yeah.
Sorry, this might be a little silly, but why do we focus so much on reducing, let's say, APSP to n to the 3 minus? What would the implication of it being n to the 2.9999?
Oh, the implication is you're going to make many people in graph algorithms extremely happy. Because even though problems like max flow and so on, we've been able to make significant progress on, this one is really, really stuck at n cubed. And there's none of the approaches work. It's very difficult. So the reason why we care about this is because if somebody can get some new technique, it will actually resolve a lot of problems in graph algorithms. It's a very, very important and central problem. All right. So back to this slide. So what I've told you is the hardness hypothesis. What I'm going to do now is I'm going to give you the most technical slide today, and it's going to be a definition of fine-grained reduction, and we'll contrast it with the reductions we teach in our algorithms courses when we teach NP-hardness. Okay? So we'll start with a very bird's eye view of polynomial time reduction. What is a polynomial time reduction? Okay, so you have two problems, A and B. Both of them are decision problems. That means their output is 0, 1, true or false. Both of them are. And a reduction says, if you're given an instance, some instance of problem A, the polynomial time reduction, menu 1, it takes the instance, runs a polynomial time algorithm, and spits out an instance of problem B. It can blow up the instance by a polynomial factor. So even if this one has size n, this one could have a size n to the 1000, but it's polynomial. And the reduction is such that whatever the answer for problem A is, 0, 1, the answers for problem B is exactly the same. So if you can solve problem B in polynomial time, you can just trivially solve problem A in the same running time by running the reduction and returning the same answer. So this is a menu 1 polynomial time reduction. These are extremely useful, and we teach them in our courses. They have many nice properties, but they have some weaknesses. So for example, in order to have such a reduction, you have to reduce between problems that have the same answer. So they have to both be, they have to have both Boolean answers in this case, because of this thing that you answer A the same as B. And in particular, imagine that I have a problem like all pair shortest paths where the answers are n squared distances. I can't use such a reduction to reduce, let's say, SAT to this problem, because SAT has a Boolean answer. Is the formula satisfiable or not? And APSP has n squared answers. So this will not work. This can be fixed with something called a Turing reduction. But the most annoying problem about this thing is this big blow up over here. You take an instance and you don't control how big the instances of the second problem get. So you do not get a relationship between the running times of the type that we want. Okay. So here's our definition of a fine-grained reduction. We start over here. We have two problems, A and B. A is the one that we believe is hard, and B is the one that we want to show it's hard. And they each have running times. Some algorithms that are very easy to come by, and one of them, A has running time A of n, and B has running time B of n. And you want the reduction to have the property that when I take problem A, an instance of it, I can translate it to problem B, so that if B can be solved faster than B of n time, then A can be solved faster than A of n time. So I have to keep the running times the same. So there's a lot of words here. So we're gonna skip the words for a moment, look at the picture, then we'll go back to the words. Okay, let's look at the picture. This is your problem A that can supposedly be solved, that cannot be solved faster than A of n time. you have an instance whose size is n, and the reduction is an algorithm. The algorithm has running time a of n to the 1 minus delta. So for every epsilon, there's some delta, and an algorithm that runs in a of n to the 1 minus delta time. It beats a of n significantly in the exponent. And this algorithm gets to call instances of problem B. So it creates these instances kind of adaptively, you can think of it. Each instance has some size, n1, n2, up to nk, and maybe this instance, to create it, you need to know what happened, what the answer of these instances is. So this algorithm calls an oracle to problem B, many different inputs, instances potentially. And once you have the answers to all the instances, you can get the algorithm figures out the answer to problem A. And all of this runs in a of n to the 1 minus delta time, except for the running time to solve these instances. Now, there's this inequality. This inequality says that the reduction has the property that the sizes of the instances of B that you create, if you sum up B of n sub I to the 1 minus epsilon, this epsilon is given to you, you will get something less than a of n to the 1 minus delta. And technically, there's a big O here and so on, but I just written like this. So what does this mean? This means that for every epsilon, if you such that you can solve problem B in B of n to the 1 minus epsilon time, I can give you this algorithm, the reduction from A to B, so that now you get an algorithm for problem A, whose running time is exactly the running time of the reduction, which is A of n to the 1 minus delta, plus the running time to solve each of these little pieces. Now, the running time for these pieces is exactly the sum over B of n sub I to the 1 minus epsilon, because that's running the algorithm for problem B on each part, one by one. Okay? So as a consequence, we get that if problem A is AB reducible to problem B, then if B is in B of n to the 1 minus epsilon time, for any epsilon bigger than 0, you get some delta bigger than 0 so that you can solve A in A of n to the 1 minus delta time. So for any improvement over B of n for problem B in the exponent, together with the reduction, you get an improvement for problem A of n, right, the exponent. So this is the definition. Any questions about this? Yeah.
Just make this the definition.
Which one?
Like the proposition. Anything that gives you this. They seem equivalent, but in general, the proposition is easier to parse, no? And
but that's not a definition of a reduction. That's a consequence of the reduction.
Can it be the operational definition? Any algorithm that results in this happening, you call it a reduction.
I think you need a definition of what a reduction is.
Do you do something with this definition?
Yeah, for example, this. Yeah, you can. There's a lot of little lemma propositions you can show. For example, if A is AB reducible to B and B is BC reducible to C, then A is AC reducible to C, and so on. You have a lot of these nice propositions, and you compose reductions and so on. Right. It's just like, when you teach courses on algorithms, you have to define the reduction. You can't just say, this is hard if one running time. You got to specify what it means.
But here, the corollary of proposition 1 of the definitions, no?
Kind of, yeah. Except you gotta care about the epsilons and the deltas and so on. Yeah, they're very simple to prove. But you gotta say what the reduction is. It's an algorithm. Okay, so the nice thing about this is that because of the way it's defined, you can reduce problems whose answer is 0 and 1 to problems that have function problems where the answer is not 0 and has many things. People often ask, well, how many instances do you get? You can have as many as you want. This K, the number of instances, can depend on n, it can be dependent on epsilon, can vary a lot. So, and the difference between epsilon and delta, they can be very different. One could be bigger than the other in both directions. Okay? Good. So here we are. So now we know what a fine grade reduction is. It's something that actually really cares about the running time and improvements over the running times. Right. So, as Sipper said, like in NP-hardness, we care about completeness. So that means we actually have a huge set of problems that are NP-complete, which means they're actually equivalent. If one of them has a polynomial time algorithm, so I'll do all of them. There's also problems that are not NP-complete, but are NP-hard. For example, quantified Boolean formulas, even the halting problem, and so on. There's a lot of these problems out there, and they're just hard because, you know, for the same reason, but they're not equivalent. So here's something we know, and I kind of stopped adding things in 2018, maybe. So it keeps growing. So there's a picture of things we know. As I mentioned, orthogonal vectors, you can just replace strong ET8 with it for many of these problems. You can show that if orthogonal vectors requires quadratic time, that even just within quadratic time, there's many problems that require quadratic time assuming orthogonal vectors. For example, if you assume SAT requires 2 to the n time, therefore orthogonal vectors requires quadratic time, and the longest common subsequence I defined before also requires quadratic time. If you can solve it faster than quadratic time, then strong ETH will be false, for example, but many other things as well. So we know a lot about these problems. There's many, many of these. Three-sum, as I mentioned, in the geometry community, there was already a huge literature about problems that are hard under the three-sum hypothesis. And nowadays, we're adding more and more problems that are not geometric in nature. Maybe there are sequence alignment problems and so on. There's many other problems like this. For all pairs shortest paths, in fact, we have an equivalence class. There's a lot of problems that are equivalent to all pairs shortest paths under these, even like subcubic reduction. So if you have a subcubic time algorithm for one of these, then you would have a subcubic time algorithm for one of these. Right. Am I running low on time?
No, you're fine.
Okay. Okay, great, thanks. Good. Okay, so I want to highlight this weird problem here. And when I tell you about it, you'll be like, what are you doing? So here's the problem. You have a graph with n vertices, and you have weights on the edges, and they could be positive, negative, some integers. I want you to tell me, are there 3 vertices that have edges between them? So they're a triangle. And the sum of the weights on the edges of the triangle is negative. Okay, this problem is very easy to solve. I can just try out triples of vertices and compute the sum of the weights and so on. And it's an n cubed time algorithm. If you could get subcubic time and to the 3 minus epsilon for this problem, just a little bit better than n cubed. In fact, all pairs shortest paths is also in truly subcubic time. And all of these are also in truly subcubic time. So really the difficulty of this shortest path problem, where it's a complicated graph and you're computing shortest path distances, really just boils down to this silly problem. And we don't know how to solve it. And this is one of those very interesting findings. And sometimes these equivalences, we've found equivalences between problems that have allowed us to get actual algorithms. For example, there was this problem called RNA folding, and we tried to show that it is hard, and we did show it's hard under some problem called K-clique that's related to triangle detection anyway. And then it turned out that you can essentially go in the other direction, and you can solve the problem faster than cubic time using matrix multiplication. So sometimes these sort of equivalences give you algorithms, and hopefully someday someone will resolve this one, and we'll get there. And then there's a lot of other problems that are actually, you can get reductions from all 3 of these problems. So they're so hard that getting an algorithm for one of them will actually resolve all 3 hypotheses. Okay. Questions here? And people like to add more hardness assumptions. I don't know. I'm not so happy about adding more. I want to collapse these, but sometimes this structure is not enough. Sometimes you have to add more. All right. So the next thing I'll do, just in a few minutes, I'll tell you about some few new developments. There will be no proofs, so I'm just gonna give you some intuition. Okay, so I will talk about the all pair shortest path problem. And in particular, what I want to know is when is it actually hard? When are the instances difficult? And the reason why I personally focus on all pair shortest paths is because I think it's probably the problem that would be easiest to resolve positively. Maybe we could actually get a subcubic time algorithm for it someday. The other two are somehow harder in a sense. So what was all pair shortest paths? You have a graph with n vertices and weights on the edges and some integers, and you want to compute the shortest path distance for every pair of vertices. There is an algorithm that runs in n cubed divided by exponential and square root log n, when the graph is pretty dense. If the number of edges in the graph is actually not quadratic, so it's n to the 2 minus epsilon, there is a faster algorithm. For example, you could run Dijkstra's algorithm from every vertex, but also even faster by Petty, 2004. You can get mn, m is the number of edges, plus n squared log n. So you can do better if your graph is a little bit sparse. So the difficult cases are when the graph is pretty dense. Another thing is if you bound the edge weights, if you say the weights are not too big, let's say they're integers that are bounded by big M, then there is actually this algorithm that runs by Shoshan and Zwick in m to the n to the omega time, where omega is the matrix multiplication exponent. Okay, I'll say what it is in a second. So Zwick also showed that if the graph is directed, you can get a higher running time, but still when the weights are bounded, you get something better than cubic. And matrix multiplication, omega is defined as the exponent, so that n by n matrices can be multiplied and n to the omega maybe plus little of 1 time. Okay, we have some algorithms that show that omega is at most 2.372. For whatever strange reason, people believe omega equals 2, which means that matrix multiplication can be done in essentially linear time in the size of the matrices. Now, one reason why people believe omega is 2 is because these running times become very pretty, okay? You plug in omega equals 2, and instead of this awful thing, you get square root of m times n to the 2.5. And here you get mn squared. So really, if omega is 2, this problem can be solved faster than cubic time as long as the weights are sublinear, truly sublinear in n. So kind of the difficult case is when they're more than linear, at least linear. Now, what if the edge weights are much larger? They can be larger than n, it could be exponential, you know. So here's something that was noticed. So Timothy Chan in 2009 said, you know what, there's too many edges out there, it's a quadratic number, but the number of vertices is only n, so what if my weights are on the vertices instead of the edges? And again, you define the weight of a path as the sum of the weights on the nodes now instead of the edges. And then he said, you know what, bless you, then if the weights are on the nodes, even if they're enormous, we don't care because you can solve the problem in n to the 2.8 time now. So the reason why the problem is hard is because the weights are on the edges and not on the nodes. Now, what does it mean for a weight to be in a node? But essentially, it's equivalent to having one single distinct weight out of every edge, out of every vertex. So imagine the weight of a node is 0 here. I can take the weight of the vertex and move it to the outgoing edges. And now we have weights on the edges, but it's only one single edge per vertex. And if you can go vice versa, if you had a single weight out of the edges of a vertex, you can move the weights on the node. So it's equivalent. These two cases are equivalent, having weights on vertices and having a single weight on the outgoing edges of every node. Okay. Euster, when he saw this algorithm, he said, well, what if we have more than one distinct weight out of every node instead of one? Then when can we solve the problem in subcubic time? Well, it turns out that you can solve it in truly subcubic time as long as the number of distinct weights out of each vertex is bounded by n to the 0.3. Okay, that's what he could get. Fine, and it doesn't matter how big the weights are, as long as the number of distinct weights out of a vertex is small. Now, every n-node graph, the degree of a node is at most n minus 1, so the total number of distinct weights out of a vertex is at most n minus 1. Right? So what we showed recently, it's under submission, that assuming omega is 2, why not? Then all pair-shortest paths can be solved in subcubic time as long as the number of distinct weights out of a node is n to the 1 minus epsilon. So n is a natural upper bound on the degree. And now if you now have a number of distinct weights a little bit less than n, then all of a sudden you can solve the problem faster. All right, if omega is not 2, you can handle 3 minus omega minus epsilon distinct weights as a cubic time. So the difficult case of all pair-shortest paths is really that you have many, many different distinct weights out of every vertex. And they can be very big, and the graph is dense. Seems kind of weird because it turns out that all pair-shortest paths in random graphs, where every edge weight is taken from the interval 0, 1, uniformly at random, then that problem is easy. You can solve it in n squared log n time. And that's in that case, the number of distinct weights per node will be basically linear. So it should be hard. And this looks like the random case, so I don't know why it should be hard. So this is why I think all pair-shortest paths can be solved faster. All right. And this is the end of my talk. Here's some open questions. One interesting one is, what if the weights are actually between just integers from 1 to n? Can you solve all pair-shortest paths in truly subcubic time? For other problems like threesome, there's natural reductions where you can take an arbitrary instance and hash its weights down to a small interval. Such hash functions don't seem to exist for all pair-shortest paths. So this is why we don't know why it's so difficult to solve when the weights are small. Can we reduce these three problems to one another? Can we show more equivalences? And there's many applications of the fine-grained approach, not only for running time, also for space, for other models of computation, like some parallel models for quantum algorithms, there's applications of cryptography where you get a worst case to average case reduction. There's a lot of these things, and we're always looking for more. So anyway, that's all I wanted to say. So thank you very much.
We have time for questions.
A couple of slides ago, you had a condition where the thing is reduced to there's a 0.3 in there.
Yeah.
Yeah, is that really a 0.3 or is there some other weird?
This depends on matrix multiplication.
Fine. So it's not a 0.3,
it's something. Fine. But now we replaced it with a 1 minus epsilon.
Fine.
Yeah. Good. Yeah.
So again, the same slide. So when we move the weights to the vertices, then we reduce the kinds of graphs we can do.
So this is a very restricted type of graph. So when the weights are on the nodes, that's equivalent to the case when there's only one weight out of every vertex. It's very restricted.
So that is the kind of graphs we're talking about in this search.
So this is the node weighted case. And now we said, well, here is only one, but Euster said, what if instead of just one, we had up to n to the 0.3? So roughly like there's n to the 0.7 weights, edges for each weight, roughly. There's very few weights out there. And here we make it so that basically there's almost n distinct weights.
Okay, but in each case, the number of edges that are coming into a vertex has to be 1 or can be greater than 1 because so the number of edges that are coming into a vertex does that have to be 1 or can there be more than?
So So the graphs are simple, so we're not considering multiple. So for every pair of vertices, there's at most one edge between them. But you can have up to n minus one edges into a vertex and out of it.
Thank you.
I think I remember for sorting problems, there's something fundamental about the structure that we can't do faster than n log n. So for LCS, do we not know something similar?
Yeah, so let me say, so sorting, there is an n log n sort of lower bound, but that's for a particular type of algorithm, in the addition comparison sort of thing. It's a comparison model. And you can break n log n once you get out of that model. So if you assume that your numbers are integers or from some range, then you can actually get linear time algorithm. And this is a problem. This is what I was saying, that we don't have unconditional lower bounds. There are lower bounds where you make an assumption, and based on the assumption, you get a lower bound, or you make an assumption about the type of algorithm you're going to be using. Once you make that assumption, you can show out lower bounds. So for all pairs that are passed, there are some lower bounds like that. And for LCS, I guess too, but you have to restrict the type of operations that your algorithms use. Yeah.
So I saw there was a slide, one slide before about the directed case and undirected case of the APSP, right?
Yeah, they're different.
It seems that so directed is slightly harder than undirected.
Yes.
So
yes.
Is there any insight or about this? And also, what if the weight is like this? General conditional hardness of like directed and undirected.
Great. Okay. So if the weights can be unbounded, then undirected and directed are equivalent. Okay, there's a way to go between them. If the weights are bounded, for example, there's one or infinity, then actually there's a very important reason why they're different, and you can actually use fine-grained complexity to show that the directed case is probably very hard under various other assumptions.
Is it because, for example, the Laplacian I'm considered about like symmetric and symmetry? So
symmetry comes into play. For undirected graphs, the distance metric is symmetric. So the triangle inequality holds in both directions, etc. Because of that, you can use that property to get faster algorithms, but you cannot do that for directed graphs.
Do you allow your reductions to be probabilistic algorithms?
Absolutely. I'm perfectly happy with randomized reductions. Yeah, and you change the assumption. Then you say that even with randomized algorithms, you cannot beat this running time, and this is completely plausible with our current understanding of techniques. But often you get a randomized reduction, and later it gets de-randomized. So often there isn't much, you can get. Simplicity, yes, you can get simplicity. Yeah.
There's a question from Zoom from our emeritus colleague, Anna Lugo, asking, is anything known about graph isomorphism with respect to set fine-grained complexity, or about the un-not problem? These are two of her favorite mysterious NP problems.
Not right now. That would be great. Yeah, but I don't know. We haven't been able to connect, in particular, the graph isomorphism to this stuff. It would be great. Subgraph isomorphism is related to all this, but it's a much harder problem. Yeah.
The last theorem that you had in your slide, is that for directed graphs or undirected?
This one, here it turns out it doesn't matter. Yeah, it holds for directed as well.
So assuming that the weights on like outgoing edges of the vertex are like distinct weights. There like this matters, right? Because it's undirected, and you can end up in a graph that has like similar weights on every edge of the graph.
Yeah, so it is interesting, but yeah, here for this theorem, we were able to do it for directed as well. Yeah. We weren't able to get something better for undirected, you could just say that, yeah. Oh, okay, so the running time is okay, I can tell you roughly how this algorithm works. So we ended up using additive combinatorics. So you take the graph and you think of it as it has some weight structure, and then you the weights are integers, and then you build a decomposition of the graph. So what ends up happening is kind of depends on the parameters of the BSG theorem, if you know what that is, Balog, similarity, Gowers. And it has if you have into the epsilon, it will be some linear in epsilon term, but it will be kind of big. Maybe, I should know, maybe it was polynomial in epsilon, sorry. Polynomial in epsilon, we weren't able to get into linear. It used to be exponential in 1 over epsilon.
Any other questions from the audience? I'll conclude with one more like kind of high level question. So right now, you know, if I had to hazard a guess, I'd say 99% of computer scientists believe that P does not equal to NP, somewhere around there. I'm curious what the status is right now, the temperatures for SET across the CS community, and maybe the spicy part. What do you believe?
For strong ATH, I think it's false. I think SAT should be solvable faster in 2 to the n time. However, orthogonal vectors, I'm not so sure. In particular, if the dimension of the vectors is much bigger than polylog, like, you know, 2 to the square of log n, it's possible that it's hard. And all the reductions will still fall there.
It's a niche opinion. Like, what % of the overall CS community do you think believes SET is true?
I don't know, maybe it's 50-50. I don't know.
Okay. Let's thank Virginia once again.
Oh, wow. Thank you. Thanks so much.
Thank you.